Welcome everybody to this week's seminar on COVID-19, the mathematical modeling of COVID-19. Today we're very pleased to have Gerardo Chowell of Georgia State University. He is a professor and chair of the Department of Population Health Sciences in the School of Public Health at Georgia State in Atlanta. He's also a senior research fellow in the Division of International Epidemiology and Population Studies at the Fogarty International Center, the National Institute of Health. Dr. Chowell holds a PhD in biometry from Cornell University, and after obtaining his PhD, he was awarded a director's funded postdoctoral fellowship in Los Alamos. Dr. Chowell's academic career has primarily focused on the development and calibration of mathematical and computational models of infectious diseases. We're very pleased to welcome him to our seminar, and Gerardo, please take it away.
Thank you. Thank you very much for the introduction and invitation. Very happy to be here. So I will be talking about some of the work that we have been conducting over the last 5 years or so with the goal of really looking into the details of the mathematical models that we use as mathematical epidemiologists, not only to describe epidemics, but also to improve them, to generate better forecasts. So let me. So this is a slide about model complexity that I think I borrowed from Ping Yan, who's I think in the audience. This highlights what you know, that mathematical models vary in terms of their complexity, in terms of the spatial structure, population structure, and it can go from simple models that assume that the population is well mixed, what we call homogeneous mixing, to models that structure the population into groups, where each group is well mixed as well. So we call them meta-population models in many cases, to more detailed models that account for commuting mobility patterns that obviously require more data, and for which the data may not be available at the time that we need. And so as obviously as we increase complexity, this increases the structure detailed of the models and increases the need for more data, additional data to calibrate them, and potentially increases also the number of parameters that we need to allow to tune them to be able to generate a particular scenario or fit the data. So there are also some statistical issues associated with the model complexity. As we have more model parameters, then we require more data to be able to ascertain well the parameters with reasonable amount of uncertainty. Because if we have a model that is calibrated to data and the uncertainty of the parameters is huge, then it's not useful to anyone, right? So we need to strike the balance between the complexity and the amount of data that we have available and the type of question that we want to address. It depends whether we are interested in only generating estimates of the transmission potential, estimate the reproduction number during the early transmission phase, whether we want to use the model for forecasting, we want to use a model to assess the effect of particular social distancing interventions, then we may need different types of models and model structure. So this slide, I think everyone here will understand very quickly, just to highlight the fact that then the building block of our favorite compartmental models is the SIR transmission structure, where the population is homogeneously mixing and every single individual behaves the same as other individuals. And as a result, the epidemics, whenever the reproduction number, the basic reproduction number is greater than 1, we observe epidemics that grow exponentially fast in completely susceptible populations, large populations, at least during the early phase, until the saturation effects take place because of the depletion in the number of susceptibles, right? And another important thing to mention is that R0, which is the most famous quantity in mathematical epidemiology, the average number of secondary cases generated by a primary infectious case during the very early phase of transmission. This quantity only applies when you have a completely susceptible population and applies during the onset of the epidemics, right? And the concept, the mathematical concept of R0 is connected to exponential growth. So the way we define R0 using compartmental models is connected to exponential growth. And that means that if we don't have the exponential growth situation, then we have to find alternative ways to be able to connect the models to the data. So if we are looking at the early transmission scenarios with, SEIR-type models, well homogeneous mixing models, not surprisingly, any type of predictions into the future will also grow in a similar fashion, and in this case, exponentially fast, right? These models are not amenable to generate other types of growth profiles. In particular, it's slower than exponential growth, such as quadratic or cubic polynomial growth that has been observed in past epidemics because of particular contact structures or behavior changes or heterogeneities. So we need to keep in mind that if we use this type of models for forecasting, if we are only forecasting the early phase in a completely susceptible population, we will get exponential growth dynamics only. So, as I said, in reality, epidemics display a wide variety of epidemic trajectories. And if we focus first on the early transmission phase, the early growth phases, epidemics not necessarily grow exponentially fast all the time. We have epidemics that can grow sub-exponentially fast, quadratic, following a quadratic growth, as we have seen, for instance, in epidemic data from China, COVID-19 recently, for Ebola epidemics, that I will mention in a few slides in the next set of slides. So social behavior, there are multiple mechanisms of factors that shape the early growth profile and that make it slower than exponential, including social behavior, behavior changes, right? People change their behaviors to avoid contracting the virus or spreading it to their family members. The particular contact network structures in the population, heterogeneities as well in susceptibility and infectiousness, because not every single individual is equally susceptible to contracting the virus or equally infectious, right? So these heterogeneities can give rise to variety of early growth profiles, and could be explained by a combination of multiple factors that are often unobserved. Here is probably the landmark example of an epidemic that grew polynomially, following a polynomial growth, in this case, a cubic polynomial in the cumulative number of cases. As you can see, this is data for the US HIV/AIDS epidemic. The epidemic follows cubic polynomial even when we stratify the data according to race groups or geographic regions, right? So even during the early phase, we are seeing an epidemic that is not following an exponentially growing pattern, as it was predicted during the early models in the 1980s. And this is a story that I have heard directly from people like Mark Hyman and from Rich Rothenberg, for instance. For the epidemics of Ebola in West Africa, it is also very apparent that the outbreaks do not grow exponentially fast, or if they do, they only grow exponentially during the very early phase, during the very early transmissions phase, comprising the first 2 or 3 generation intervals in the best scenarios. And when we look at the data disaggregated at the subnational level. These epidemics are asynchronous, so they are occurring at different times in different places. And when we aggregate the data, we may get something that could look more exponential. But in reality, we are losing a lot of information when we do this aggregation process, that the epidemics that are actually affecting the population are not occurring at the same time, but are occurring at different times, different places. It's like a wave of disease that is moving through the populations. And I think that the key here would be to predict how this wave is moving through the populations, what are the mechanisms and what are the factors that are driving the timing of these outbreaks in the population. So realizing and making aware about these patterns is important as we develop these models and we account for these patterns in transmission. So in order to understand better how these growth profiles, cell growth profiles behave and quantify them, we can modify the Malthus equation and aggregate what we call a scaling of growth parameter or the acceleration of growth parameter to be able to quantify this parameter P, a number between 0 and 1. So P equals 1 if we have exponential growth, P will be less than 1 if we have sub-exponential or polynomial growth. And the nice thing about this is that we can actually quantify the parameter uncertainty, right? We can have a P estimate that may include the exponential growth regime, right? So you can have a P of 0.8 that spans, you know, all the way from 0.6 to 1. And so you are actually accounting for the uncertainty in the growth profile, right? So it doesn't have to be exactly quadratic or cubic, but you can have a range, a continuum of epidemic growth scaling. These are some examples of the type of growth patterns that you can obtain from this model. This is an example where you can actually show that by accounting for the actual growth profile, you can do much better in terms of predicting in the short term what's going to happen. This is the 2009 foot and mouth disease in the UK data, right? So you can see how the growth profile never reached any type of exponential growth. By using this model, you know, you can see quickly how well the model is constrained to the data and is able to capture the right growth scaling. In this case, it's about 0.6. I'll show you in the next slide the estimates. And how, as we move forward, the model is able to ascertain better that P parameter, right? More data, right? That means less uncertainty in the parameter estimates, as long as the model is able to describe the data well. And then the uncertainty in the forecast is also reduced. So you can see, for instance, in panel C here, how well it's capturing in D and E. Obviously, this model will predict well the growth phase of the dynamics, but it will not predict any type of saturation point or a peak in the curve, because this model is only designed to characterize growth patterns, right? So I'll show you in the next slide how to characterize the rest of the epidemic, not only the growth phase. And this is slide I was mentioning, the scaling of group parameters around 0.6, and you can see how the uncertainty bounds quickly are reduced, right? Uncertainty, as you are using more and more data, right? So when we use about 30 days of data, this P parameter, right, is about 0.55 all the way to 0.7. So what mechanisms can give rise to this early sub-exponential growth? As I said, there are plenty of mechanisms, but now we can put them also in some terms of mathematical models. For instance, the transmission rate is not necessarily constant, right? Because people quickly change their behaviors as soon as they know that there's a new pathogen. And, you know, if the pathogen is generating severe disease, we react even with more changes to our behavior, because we don't want to get sick, we don't want to die, we don't want to pass the disease to our family members. And so you can see here that even with a small change in beta, as long as the decline is in this case exponential, but you can play with different types of decline functions. This growth pattern, right, is no longer exponential, which is this log in log scale straight line, but it follows some saturation, right? So even if Q is 0.005, you can quickly bend the curve, right? So if our models assume a constant beta, you are only tracking this type of pattern here. So we need more flexible models that can account for these changes over time. In this case, the change is due to a reduction in transmission rate as a result of behavior changes or interventions. And then we can translate that concept into compartmental models that, you know, many researchers have been developing to characterize and study the COVID-19 pandemic. This is one of them, where we have incorporated the role of asymptomatics, the role of exposed individuals in the first and the second stage, the role of testing, right? Because we are only testing a fraction of the symptomatic individuals. And then importantly, the transmission rate here, right, declines, not immediately, but it declines after a brief period of exponential growth, right? So it declines after the intervention is put in place. And actually also, we consider a decline in the contribution of people in healthcare settings, hospitalized individuals that could be generating amplification of disease there. So by doing that, we can, these and other models have been able to fit some of the early transmission patterns of the COVID-19 pandemic, particularly in China from the very early days. Here's an example of the fit to Guangdong, China, right? Very nice fit. We were, you know, very surprised that these relatively simple models can fit this type of single peak epidemics, right? This is all China, all provinces excluding Hubei, right? As you know, Hubei is the epicenter, was the epicenter of the pandemic in China, where again, it really fits the data very well. And by fitting the model, we are here fitting the transmission rate beta, we're fitting the proportion of people, estimating the proportion of symptomatic people that are detected and tested and brought into isolation. And then we are also estimating alpha, which is how quickly we're able to diagnose individuals, which is a critical parameter, a parameter that you know, has been recognized as a very important from the, you know, back to 2003 during the SARS outbreaks. That was one of the main findings that was obtained from this type of mathematical models. So you can see here the fit of the model to South Korea as well, right? But in here, I'm showing you the cumulative curve, right? I'm not showing you the actual daily number of reported cases. So the model fits very well. You can generate a short-term forecast here. But when we start doing this type of cumulative curves, unfortunately, as you know, we are missing information by aggregating data and looking at the cumulative curves. Because if the epidemics are showing multiple peaks, right, we are not going to be able to see that clearly in this type of cumulative curve forecasts. We want to look at the data at incidence data, right, instead. Here's another example with Italy, where, you know, the model obviously fits nice, the very early transmission phase, and you can use it to generate forecast for the very near future. Another mechanism that can give you rise to a slower growth than exponential is space, right? If we have a well-constrained spatial structure, like in here, we have a population where we have two levels of mixing. People are mixing within their household and within a community. So a group of households make a community. Then we are constraining the interaction of the individuals, right, in the population. By doing that, you can get a wave of disease that is moving through the population. And this wave will not be necessarily spreading exponentially, right? Obviously, you can regulate this type of wave, right? If the community spans the whole population, then you can retrieve exponential growth again. But if you can modulate the size of this community size, you can play with different types of early growth profiles. And that makes this model a very interesting and useful tool, I think. So you can see here how the community size, when community size is small, 25, quickly, right, you see how the model predicts sub-exponential growth dynamics, right? This is incidence data. The red curve is the average. The black curve would be the predicted growth for exponential growth, right? Which is not happening here. This is just to contrast that. As you increase the community size, right? So you get a little faster growth, right? And then here, C is 65. So 65 households, that's what I mean with the community size. You start to accelerate this type of the early growth profile. And another point to make here is that if you don't have exponential growth, right, the reproduction number is actually a function. And it's a function that declines asymptotically towards 1, right? So whenever you have something that grows slower than exponential, that reproduction number will decline asymptotically to 1. And that's something that we can show mathematically, and that's something that we published in this paper in the interface. So what happens to R0 with early sub-exponential growth? Oh, that's what I was telling you. So if P equals 1, right, then this is a formula that we know very well, right? You can get R0 by looking at the growth rate and the generation interval. But if P is less than 1, this is the result, indicating that this R is a function of the generation G, and that this is a function that declines over disease generations, right? These are the examples. This is an example with real data. This is the Ebola in Western area urban. So where you can see clearly the model, the generalized growth model is, fitting a line here, linear growth almost, right? And that is reflected here with the P of 0.5. But still, you have quite a bit of uncertainty. P, the estimate of P goes from around 0.3 to 0.7, right? But you can capture that uncertainty. And by the way, this is assuming that the error structure in the data is Poisson, right? And then this is translated into this estimate or this distribution of the reproduction number, right? The mean is 1.3, and then you have this confidence interval that is linked to the uncertainty in this growth profile. As you use more and more data, right, because this is not exponential growth, as I was telling you, sorry, the R will tend to decrease, right, consistent with the theory of exponential growth dynamics. Now, let's move beyond the early transmission phase, okay? In addition to having epidemics that not only not grow exponentially fast, we have epidemics that show structures or trajectories that are very different to single peak epidemics, right? Like the one that I just showed you for the COVID-19 in China and Hubei. The curves are showing clearly one single peak. And to me, that gave me reassurance that this pandemic, we were going to be able to control this pandemic easily with some level of contact tracing and doing some public health interventions, but moderate should be probably okay. But I think this highlights the intense interventions in the the best case scenario, the interventions that the Chinese government put in place, to some extent obviously draconian, and at the multiple levels, not only with the lockdowns but also with face mask wearing and temperature checks at any entry point to places like supermarkets. I think that played a major role, and that's the reason why we saw a single peak. So looking at the data from China, I think most models thought that we were going to be seeing single peak epidemics in the near future, which is not the case, right? As I will show you. So this is a slide is used to highlight the fact that epidemic trajectories can display multiple peaks, multiple modes, right, are multimodal. And sometimes these peaks are very close to each other that we don't see them with our naked eyes, right? So if the peaks are strongly overlapping, they may be very close together. We don't see them unless we have additional data at a finer spatial resolution to be able to see, hey, there are 2 or 3 peaks here that are overlapping with each other. If the peaks are weakly overlapping, like in this case, obviously you can see here clearly that there are 2 peaks, right? One here and a smaller one here, right? So these patterns result from the aggregation of multiple spreading phenomena, right? You can have sub-epidemics that are affecting a particular place in one population, right? It could be affecting the north part of the city. And then you can have suddenly another outbreak starting in the south part of the city. Or you can have sub-epidemics, like in the case of HIV/AIDS, that are affecting a particular communities. For instance, the MSM, right? Or injecting drug use. In some cases, you can have generalized HIV epidemics where you don't necessarily see the sub-epidemics because they are overlapping with each other so well that you can characterize that as a single epidemic, right? So basically you have epidemics that are on top of each other. So in reality, sub-epidemics are occurring at different times in different places and may be driven by different mechanisms, right? In the case of COVID-19, obviously, I'll tell you in the next slides that that's happening. Let me tell you about the DRC Ebola epidemic, right? That was recently brought under control, which is very good news. You can see here that the pattern is characterized by multiple peaks and valleys, multiple sub-epidemics affecting different places, and likely these sub-epidemics are driven by violence, right? As you know, there were multiple violent events attacking healthcare workers and treatment centers that, you know, precluded the early control of this epidemic. So there are multiple mechanisms that can give rise to this type of patterns. Very different pattern, right, to what we have seen in the past in West Africa or in Central Africa. So again, when something is spreading in the population, there is a transmission process underlying that epidemic or outbreak, right? But we don't observe really what's going on. We only are, you know, counting cases. In the best situation, we have counts of cases at, you know, sub-provincial level or county level, right? But we are not seeing how one case is giving rise to 2 or 3 or 4 cases. We are not seeing the transmission tree, right? It's nearly impossible to predict, particularly when you have a large outbreak that is quickly spreading to the population. And so this figure on the left is highlighting exactly that you can have a situation, right? You have the market generated multiple secondary cases, and then some of them generated 2 cases, some of them generated 1 case, right? But you can have a different situation in the middle here, right? Perhaps with the second generation of cases generating more cases on average, or you can have another situation like so here with multiple generations, but, you know, each generation generating super spreading events potentially. But at the end of the day, we observe this curve here in the bottom, right? We observe the trajectory, the incidence that can show multiple peaks, but those peaks could be the result of completely different transmission trees. And on the right, this is the outbreak of 2003 SARS in Singapore. This is actually a transmission tree that Ping Yang put together for our book recently. And you can see, you know, that this is a very nice transmission tree, very detailed, you know, put together by Go in that publication. When you extract the incidence curve from here, you see clearly an epidemic curve with 2 peaks, right? The most salient feature of this outbreak is that the first peak affected a particular healthcare. Okay, good. So last year, we developed this sub-epidemic wave model with the goal of trying to capture epidemics that are made of the composition of sub-epidemics that may occur, at different times, but could be overlapping with each other. And by doing that, we can capture a lot more complex transmission patterns than what we can do with simple models, with simple logistic type or simple SIR-type models, or are more amenable to capturing this type of patterns, and also importantly are useful to generate forecasts. And I will show you how these models are performing. So briefly, this is a system of differential equations, right? So I is the index for the number of sub-epidemics. This is, this is the same type of growth pattern that I showed you earlier, generalized growth model. But now the next sub-epidemic, the sub-epidemic I, takes off whenever the number of the cumulative cases in the previous sub-epidemics exceeds a threshold that we call C sub THR. Yeah. So in this case, red is one sub-epidemic, blue is the next one. And so the sum of the two is the aggregation, which corresponds to the gray lines. And you are seeing multiple lines because each line represents the uncertainty in the parameters, right? So you can have a combination of multiple shapes in some cases. And you can see here the third sub-epidemic is starting to grow, but it's not clearly yet apparent just from the data, right? From the aggregated curve. So it's nice. This model is I think it's nice because you can also characterize the size of the wave, right? With a closed form formula right here, right? Because it's the sum of an exponentially declining sub-epidemics, as you can see here, where n is the total number of sub-epidemics, and K0 is the size of the first sub-epidemic. So the next sub-epidemics, consecutive sub-epidemics, are actually declining as we move forward in time, right? So with this model, 5 parameters, right? Let's review that. The scaling of growth, the growth rate here, the threshold, and the size of the first sub-epidemic, K0, and how quickly the sub-epidemic sizes are declining, right? Because we're assuming that there is a wave, and at some point that wave will go down. It's not going to stay there forever. So you can see here in the first example in the top panel, if you have sub-epidemics that are overlapping with each other, strongly overlapping, you can give rise to this type of stationary wave of disease moving, right? So the red curve corresponds to the sum, the aggregation of the sub-epidemics, right, from this model. You can get this type of stationary wave, right, which is actually something that we are seeing in some of the data of COVID-19 pandemic in different settings at different spatial scales I'll show you. The second one is the same, except that, there is a limited number of sub-epidemics because the, population size is limited. The third one is, it's actually showing the impact of interventions, right? The sub-epidemic sizes are declining over time. The next one is the same as above, the top panel, except that now the sub-epidemics are less synchronous, okay? Are weakly, what I call weakly overlapping sub-epidemics, right? So you can now see here clearly, there are multiple modes of the disease, compared to the first panel where the sub-epidemics are so overlapping with each other that you don't see those modes, those peaks clearly, right? So we estimate the parameters using a parametric bootstrap approach, right? Assuming that the data has a particular error structure. So it could be Poisson error structure, or you may introduce a more complicated error structures depending on the data. In this situation, the model is fed to the data, and then we generate additional synthetic data to be able to generate empirical estimates of the parameters, right, with a particular error structure. We started using Poisson error structure at the beginning of the epidemics in other parts other than China, but then later we realized that Poisson error structure was not sufficient. There was a lot of over dispersion for multiple factors, right? including the varying testing rates over time or changing the reporting schemes. So we had to ramp up this over dispersion in the error structure. And as I said, we need only 5 parameters, right, to characterize these epidemic trajectories. So there are different performance metrics, right, that can be useful to assess how well the model is fitting the data. And this is useful when you want to go ahead and compare how well this model is performing relative to another model, right? So metrics that only account for the mean of the predictions are the mean absolute error, mean square error, right? But other type of metrics that account for the uncertainty include the prediction interval, right? And a very useful one, I think, is the mean interval score, because the mean interval score not only penalizes for wide, it penalizes for how wide the prediction interval is, right? So if you have the tighter the prediction interval, the better the score, right, for that model, right? And so the score is measured based on how your data is scattered around this prediction interval here, right? So here's an example, the SARS outbreak in Singapore, the model is able to detect that there are 2 modes. You can see here clearly in the top and the bottom, right? This is the uncertainty of the parameters, R, P, K, and Q. This is the figure that I had showed you earlier, the 2 peaks, right? So that's nice, it's able to get this. We also fitted it to the main wave of the plague epidemic in Madagascar, where you can see that there are strongly overlapping sub-epidemics for this epidemic. So it's nice to see that, and the model fits very well. This is the model showing you how well it's forecasting, at least in the short term. And then I think the point of this slide is to show that the model is already predicting that you need additional sub-epidemics, right? The vertical line is separating the calibration on the left from the forecast on the right, right? So it's clearly showing that there are additional sub-epidemics coming up in order to fit the data, right? So whenever you start to see this type of leveling off or a plateau, it's just suggesting that there are other sub-epidemics coming up. You are not seeing them, but you need them if you want to fit that data. And then that's very productive, because then the forecast is actually better, right? This is only 4 weeks ahead forecast as an example. And then we can show, right, maybe not surprisingly, that the model is actually doing better than models that give you one single peak. Here's another example of the Ebola epidemic in DRC, where you can see that the model captures this stationary, leveling off or wave of moving wave. It's nice to see that as you have more and more data, actually the model is able to predict that there are some cycles here, some regular pattern here, right? And on the right, you can see the sub-epidemics. So this panel corresponds to this panel. So you can see here the first sub-epidemic, second, third, and fourth. And so this is useful to generate the short-term forecasts. It is another example where you can see clearly that, the epidemic was going down, but there was a second outbreak coming in, right? That the model is predicting that you need this sub-epidemic to be able to forecast the future, right? So that, I think that's a very powerful feature of the model. So we have been doing forecasts using various models, including the sub-epidemic wave model. We have been publishing them in our website at Georgia State University School of Public Health, with the help of Homa Rafi, who is our communications person, who has been working very hard with us to put this information out there on an almost daily basis. Let me show you some of the forecasts that we have been generating more recently. This is Germany. Let me check just my time. Okay, this is Germany, right? So different colors are showing the different sub-epidemics, and this is the sub-epidemic wave model. One thing that I cannot mention is that we have been developing this further, the model, to incorporate different types of decline functions. For instance, a power law decline function rather than an exponential decline in the sub-epidemics. Sometimes that power law gives you better forecast, like in this case. This is the first, the second, the third, and the fourth. All of these colors, as I said, are the different uncertainties that are coming from the bootstrapping approach, which make the approach, I think, powerful. The model is able to fit the data. You know, there's a lot of variation here, and we have to assume that there is some level of over dispersion because, you know, the numbers are fluctuating quite a bit, but the model is able to capture these patterns. This is the same as before, but this is what you get once you only look at the prediction intervals, right? So this is May 10th. So this is something that forecast that we actually generated very recently. And so you can see the forecast is that the tail will continue in the near future. And this tail may just continue at some low level for a long period of time. This is a 20-day ahead forecast, by the way. For France, we have a similar situation, although you can see these very high data points here, a lot of noise that maybe, you know, the result of backtracking and adding cases that, you know, were not reported in the past and things like this. But overall, the model is fitting the data well and is predicting a low wave in the future. Spain, I think this is very interesting, the Spain one. You can see how for Spain, we predict 2 sub-epidemics that are not overlapping too much with each other, so that you can see that there are clearly 2 modes, right? One peak early here, and another one here. And then this forecast was conducted on May 3rd. This forecast is showing that in the future, expect the next resurgence and the next sub-epidemic, obviously smaller than the next, but it's coming. This pattern here downwards is not gonna go straight to 0. That's what the model is predicting. So let's look at the next forecast on May 10th. Indeed, there was a resurgence, right? Which is what we had predicted here. So in this instance, it's working very well, and the model, as you can see here, is fitting the data, capturing the uncertainty fairly well, and we have been a little bit more confident now to generate 20-day ahead forecast rather than just 10 days. And importantly, point out that we are fitting and explaining the data all the way back to February 24th. We are on May 10th, right? That contrasts with, using models that only are grounded on data on the last couple of weeks, and then let's move forward. Right? We're showing how the model is predicting the past, has described the past, and then the future. Right? So I think that's important. If we are using models, we need to show how the models have been describing the data, because if they have not been able to describe the historical data, how can I support a forecast in the future? Right? This is for Canada. So all of my Canadian colleagues and friends are very interested probably in this one, which actually we are publishing on the website. You can see here that the model is predicting like a stationary wave. For a while has been predicting this type of pattern here. And you can see these grade curves over here, suggesting that there is a chance that you can see a resurgence because of the sudden synchronization of some of the sub-epidemics. And I think that's pretty cool. Right? Suddenly, as you project forward, the uncertainty, the synchronization of the sub-epidemics collide and become more synchronous and can give you this type of pattern. Now, if we look more recently, that was May 3rd. If we look at May 10th, 7 days later, it appears that this is going down. So hopefully that's the case, that finally from going into this leveling off mode, there might be a downward trend in the near future, according to this latest forecast, okay? Obviously this data point here up here, I don't like it, but what can I do? I don't know why this very high point was reported here. I think Ping Yang can tell me what happened there. So this is the forecast for Canada when you only want to look at the prediction intervals, right? If you want to look at what's going on inside the hidden dynamics, this is the picture. The UK on May 3rd, we were predicting that there's more to come. This is not going down. In fact, it looks like you may have another hump, another wave. There's quite a bit of uncertainty. Now, May 10th for the UK. Finally, it looks like you may have still more disease, but a slight decline in the size of the next sub-epidemic. And that can be seen if we look at the prediction intervals, right? Still, it's pretty high, but there's some decline in the overall incidence level. The Netherlands, this is another example where we had substantial period of time with a lot of, with a stationary form here, like a leveling off. Finally, May 3rd is indicating that this is going down. Now let's look at May 10th forecast. The downward trend continues, okay? That's the prediction. Now for Italy, there's something interesting happening here. The suddenly slowdown here, right? This trend was going down here. The sudden decline here is not well in line with the model. So something is happening here. This is like a linear decline, whether that's because of slower rates of testing or something. I would like to understand. But the model is still predicting, don't hold your breath because there's more to come. There's a longer tail of the disease coming. And that's what we are seeing here on May 3rd and on May 10th. It appears that the model now is overestimating Italy. We'll see, I want to see the next, but right now the model is saying, I am holding this forecast, although I already have a bunch of points here outside. So this is a very interesting case where you see here an interesting decline, faster, much faster than what I would think, after seeing many curves, many shapes, my brain tells me that something is going on here. And for the United States, I literally love this article because this goes very well in line with the sub-epidemic wave analysis that we are doing, right? That if you look at the data, aggregated data at the national level, you are going to miss a lot of details, right? And the spatial heterogeneity. So on the left, the entire US as of May 3rd. On the right, this is the US, but then you separate New York City from the rest of the US, and you can see that the actual pattern for the US is going up if you remove New York City, right? So it depends on what you are looking at. And so this pattern here is the result of the aggregation of sub-epidemics. Here's one, here's another one, right? And the SIR models, compartmental models or metapopulation model, we have a lot of trouble trying to get this type of patterns. I would like to see how we can generate these two sub-epidemics using those type of models. We're working on that, but we haven't been very successful. And the problem is that these sub-epidemics are not necessarily following a particular mechanism, but they are occurring more randomly, right? And are popping up at different times. But the most interesting thing is that when you aggregate them, you get this type of structures, right? If we look at the state level data in the US, these are the fits and the forecast. This is the USA as of May 10th. It's showing that there's a stable pattern here. We will see, because as you know, many states in the country, in the US, have already reopened their economies. So we will see what happens in the next 20 days. I think by the end of the month, we should be seeing a departure from this pattern, right? Unless we have been able to live with the virus by wearing face masks, by keeping a distance, we're gonna have to see. But this forecast, the way we should interpret this forecast is, if the pattern continues, right, with the same rhythm as before, this is what we expect to see. Any departures from this forecast will likely be the result of the lifting of the interventions and increased contact rates. I think this forecast right now serves as a benchmark to compare against in the near future. This California, Florida is going down. Georgia is stable. It's still stable, although, we have been reopened during the last 10 days or so. Michigan is low decline. Maryland, stable. Louisiana, which was the state with the largest growth rate in the world at some point. Now, it's going down, is a relatively low incidence pattern. And these are the sub-epidemics, right? For the same graphs, but now I'm showing you the sub-epidemics, so you see the structure and how things are looking into the future, right? In the number of sub-epidemics. Obviously, these sub-epidemics are not explained by a particular situation, right? Whether it was a nursing home or the state didn't close schools early enough, but it's a combination of many factors. And so we argue that the model is able to capture the macro scale picture of the epidemic. And by doing that, it's useful to generate forecasts in the foreseeable future. This is Montana, New Jersey. It looks like New Jersey is going down. That's good. And New York as well. Clearly, New York is going down, very well in line with the data. Oklahoma, pretty stable. Look at this, right? Rhode Island, South Dakota. South Dakota, there's another second wave here. Texas, stable. You may even see a resurgence here, interestingly, right? You have a bunch of lines here. Washington State is going down, although the next wave is coming, including the outbreak in the White House. So I think, is that it? Oh, sorry. And I think just have a couple of minutes now. I basically focus on the sub-epidemic wave model because that's the model that is doing the best performance right now. As far as I know, it's the only model that is being generating these forecasts for which we're publishing not only the forecast, but also how well the model is performing, how well the model is fitting the data, and not only looking at the cumulative trajectory, but also looking at how the incidence pattern is being captured by the model. I'd like to acknowledge all of my collaborators. Hopefully I'm not missing anyone here who have contributed in one way or the other to all of this work. And my PhD students who have been very hard workers during this pandemic, very grateful to them. Kimberly Rusa, Natalie, and Giselle Lee. And I'd like to advertise the book with Ping Yan, obviously. I think you all know about it. But most importantly, I would like to dedicate this talk to Babak, who was an excellent mathematical epidemiologist and played a very significant role in the mathematical modeling community during the last decade or two. And he passed away recently. And yeah, I was very sorry to hear that. So I dedicate this talk to him. And I look forward to editing a special issue on his memoriam. Thank you very much. Thank you.
Thank you, Gerardo. So again, thank you very much for dedicating this talk to our colleague and friend, Babak. Actually, there are a lot of very active discussions behind your talk, and quite a number of discussions, some of questions. Let me start with Kevin Brown. Kevin, are you able to raise a question directly?
Sure. I guess my question is, these models are kind of inferring sub-epidemics. Have you considered ways of validating, whether the mechanism that the model kind of presupposes that's driving incidence pattern is actually the true mechanism that's being observed in the population, and how would you go about doing that, I guess?
Yeah, it's a broad scale mechanism, right? I'm not telling you exactly what's the nursing home or what's the hospital that is contributing to a particular sub-epidemic, but I can tell you that the pattern is the result of the aggregation of sub-epidemics, that you need additional sub-epidemics rather than just one sub-epidemic or one single, peak epidemic model, but you need more than that in order to predict, for instance, this type of stationary wave, right? If you try to fit this to a single epidemic, you cannot get this stable mode, this stationary wave. You need additional sub-epidemics that are growing. And as a way of validation, I show you the fit of the model to the SARS outbreak in Singapore, where you have two sub-epidemics, right? Basically explained by amplified transmission in two healthcare settings, right? Or the situation in the United States, where you see these two spikes here that are the result of sub-epidemics that we are not seeing, right? So whenever you see something that is in a stable mode, leveling off, it's just telling you that there's something underneath that is still growing, right? And you need this additional epidemic curve or sub-epidemic to be able to explain this pattern. That a single sub-epidemic model, a single epidemic model will tell you that this will go down right after this peak, right? Or maybe, yeah, you tell me, compartmental models that can give you this type of stationary wave. You can get that, right? But you need to invoke mechanisms such as rapid replenishment of the susceptibles, right? For instance, you have a population that the susceptibles are leaving and coming in very quickly, right? To be able to maintain that pattern. So basically you want to get an R around 1. So the mechanism is, it's a macro scale mechanism, and it's basically the need to invoke for multiple sub-epidemics that are not synchronized, but asynchronized. But when they get aggregated, they can give you this type of broader, more complex patterns.
Yeah, that's very helpful. I guess just a quick follow-up question, which would be, well, how do these different levels of models, so you are actually applying the model, at the level of the United States, and then as well as at the level of, the states within the United States, say, how, what is the kind of rationale for doing that, and how do those models actually kind of nest, how do the state-specific models nest and provide an estimate of the overall, US epidemic, I guess? Like, what would happen if you kind of reaggregated your estimates across the states to the level of the United States? Would those provide different estimates?
Oh, no, that's a great question. Actually, one avenue of research that we are pursuing here is also, when you disaggregate the data and when you aggregate it, can you actually forecast better the national curve, right? Rather than taking the whole national curve, you do the forecast first at the state level, right? A final resolution, and then move up to the national level. And that may be giving you a better forecast. So we're exploring that idea. Now, I think that's part of your question. But what I can tell you is that if you aggregate the state level forecast, will align roughly well with the national curve. Not exactly, but
Thank you.
Thank you.
Okay, so I have, Ping, you want to make, have the next question from Noticia, but Ping Yan, you have a few comments you want to make?
Okay, so can you hear me?
Yes.
Yes.
Okay, so first I will answer Gerardo's question about a specific outlier in the data.
Oh, thank you.
And that point, there's a very high point. And I can tell you from the public knowledge, it was on the news. One specific province in Canada, they had actually all the provinces in our computer systems are a little bit out of date. Like it's not very clumsy to operate. And one province decided to switch and revamp the system, and that caused a computer glitch in April. And then by the end of April, when everything's up and running, they put a huge number of cases on that single day. If that glitch had not happened, it should have been spread out throughout the entire April rather than put on that day. So that is one example. And another problem is in all of your analysis, we have to understand how data are generated and reported. And so I give you the example in Canada is that even in different provinces, they all say something called a case definition. But this case definition may not be consistent across different jurisdictions. And even within a single jurisdiction,
Pink, I'm losing you.
Defined over time. For example, sometimes they only put they call it confirmed cases, and sometimes they have both confirmed and probable cases, and sometimes it's purely based on laboratory results, and sometimes they may say if they are IP linked with a case, and this link has obvious symptom, would define as a case. So these kind of definitions are changing over time. That gives you a lot of a problem. That means we really have to understand how these data are generated rather than just taking the face value. And secondly, all those publicly available data are by date of report, which is quite a few days away from, let's say, the date of symptom onset. Maybe not a few days, possibly a week or more than a week away. If you think about it, there's another incubation period before the symptom onset. So I would imagine whatever you see, these curves may be a reflection of what happened 10 days or even 15 days ago. And what is really happening now may be observed sometime in the future. So there's quite a long time delay. And I will talk about this possibly next time if I have.
Right.
That's the point.
Completely agree. You know, I think the consequence of having, you know, call it suboptimal data because of all of the issues that you mentioned, a consequence of that is that the uncertainty in your predictions will be broader, and you know that you pay the consequence by having prediction intervals that are, you know, wider than you would have if you had the best data, right, as you're saying. So that's why we have to introduce hit-over dispersion in order to capture all these variation resulting from, you know, the weakened effects and the case definitions and the lack of reporting for a particular period. And that's the only way to be able to capture the patterns. Is there a particular province in Canada that is doing the best job, Pink, in putting together the data set? Is there any one that you?
So I would like to postpone this discussion to next week because good news.
Okay.
Ping Yan, your collaborator, is going to talk next week. So I invite Gerardo to join us. You can continue your debate with Ping Yan and discuss.
I will. Thank you so much.
Next week. So the next question is from Leticia. Am I right? Leticia? Can you raise the question? Or you say you have a couple of questions, Leticia, Ramirez? My apologies.
Am I supposed to read them? Or
Thank you.
Yeah.
Thank you, Gerardo, for the work and the presentation. I don't know if you can go back to the slide when you present the sub-epidemic model, please.
Maybe this one?
Yes, that's right. That one. Yes. You have a lot of flexibility, and that's pretty good. And you're able to capture what in reality we observe, these different waves. But I would be worried about the identification problem. How can you assure to have a model that is in which you can identify all the terms? Or in the case of Canada, you show us one model, and once you update it, it's very, very different.
Yeah, yeah. Okay, so there are two questions. One is related to identifiability of the model itself, and the other one is, you know, what happens when you have a lot of noise also in the data in Canada and all of the countries. Right, so that's an excellent question. The model is actually able to characterize very well or identify the sub-epidemics very well, and in part is because of the limited number of parameters that we need to fit. Obviously, as the sub-epidemics get more and more on top of each other, more overlapping, right? You will have more trouble, more difficulty being able to separate them. Because if you have two sub-epidemics on top of each other, you might as well only fit one single sub-epidemic, but double the size. Yeah, you agree with me? So it depends on the shape of the structure. But if we are talking about the identifiability of the model, it is pretty good, I would say. And that is influenced also by the noise in the data. Like in Canada, you know, one data point that quickly grows, the model may take that as a next of epidemic when it's only noise, right? It's an artifact that you pointed out. You were going to ask something else?
Yes, it's the thing is that I don't see few parameters. I see a lot because you have n different, like I goes from 1 to n.
Oh no, the power, yeah, no, the power here is that we link the sub-epidemics, right?
No, the power, no, the sub-index, the I sub-index.
Yeah, you can have 1,000 sub-epidemics, but you only need 5 parameters because the next sub-epidemics are declining. You see here the K, for instance.
Mm-hmm.
The size of the sub-epidemic is the only thing that is changing for every single sub-epidemic. The growth rate, the scaling of growth is the same, right? So you don't need any additional parameters. Mm-hmm. So the number of parameters is, I'm glad you asked this question, does not scale with the number of sub-epidemics, right? You need the same number of parameters whether you have 3 sub-epidemics or 300.
Okay.
Yeah, thank you.
Okay, I have a last question from David Milbury. David?
Hello, can you hear me?
Yes.
Yes.
Sorry, oh, thank you. First of all, I'd like to thank you very much for the talk. I really appreciate it. My colleague and I, Jerome Levesque, just joined some of the modeling group here in Canada. We're coming from the world of operations research, and so we're just trying to lend any help that we can. One of the things that we've been interested in, because it fits well with our operations research work, is branching models, and particularly branching models in small settings where you have a hotspot that just ignites something like an old age home, perhaps a military base, perhaps how do you see branching models in the early stages of an outbreak fitting with the work that you're talking about with getting into sub-epidemic waves and work that you're working on?
Yeah, no, that's a great question. There is definitely a connection here. They are at different scales. I think the branching process models are at a finer scale than this. And for instance, if you think of a continuous time branching process like the one that we described in the book with Ping Yan advertising, you actually have small sub-epidemics, right, that are occurring early on as the epidemic progresses, depending on the shape of the generation interval distribution, right? So the next generation generates the next set of secondary cases, and the timing of infection follows a particular shape of the generation interval. If the generation interval, for instance, follows a gamma distribution, right, you early on will see like little blips or like gamma distributions, right, that are growing over time and that are overlapping with each other. So there is definitely a connection here. But I think this model works better at the next spatial scale, right? Because in the situation of the branching process, you have like small sub-epidemics that are actually growing over time. And this model, I think, works better when you aggregate all of them together, generate the first sub-epidemic that drives the growth. But
thank you very much. That's good. Yeah.
Definitely, there is a fruitful area of research right there, connecting branching process models with larger scale models. I think there's definitely, this is something that I have, discussed, fun discussions with Ping Yan, and I think there's a lot of work to be done here. Yeah, thank you.
Well, we'd like to discuss with Ping as well. We're really excited about that kind of work, and we're very happy to be part of it.
Great.
Thanks.
Thank you.
Thank you, David. So I think given the time, I think we should not continue more discussions, and I will be happy to forward you further questions to Gerardo and Conway, and we can probably discuss this further.
Yeah.
I'm sorry, who is? Yeah, so otherwise I would suggest we stop here, and thank you, Gerardo, for your very interesting talk and for your continuing work in the subject areas. So
thank you, John, and thank you to everyone for organizing this.
Thank you. So the talk is videotaped, so you can have access after the talk as well. Thank you very much again. See you next week.
See you next week. Thank you. Bye.